This video, we're looking at a simulation of a transistor, and we're studying its IV, its current voltage characteristics, using Multisim. So we have, here is our transistor, the base collector-emitter, and we have a battery that is coming into the base, and then another different battery, a larger battery, coming into the collector, and measuring the current coming into the base and the sort of from after the resistor. So this is the base to the emitter, and then we have another voltage that is the collector to the emitter, and what is the current that's coming down, sort of the collector-emitter current. I've been varying this V1, keeping everything else fixed. And so I'll fill in that missing 1.1 and then maybe one other. So 1.1, okay, and turn on the simulation. And so this was, that one must be wrong. I must have an extra 0 on there. We'll confirm that in a second. 685 for this. Oops. I'm right now down here at, if I don't know, I will get back to, this was 0.041. Here the VCE is 1.426, and the current is the 8.574. That 1 volt results, where I've got the wrong number for this voltage, 0.678, and the 032, the others were right. Let me show you a 1.7, get one more in that direction, and then I'll go back and do one of the low ones, redo one of the low ones just to show you that. So this is 0.69. It was 0.101, 0.15, and 9.85 here. And let me go back, and this one that is yellow, the 0.3 was giving me a current of 0, and at some point I'm going to divide by a current, and I didn't want to divide by 0, so I just kept changing this sort of battery voltage until to get me away from that point, which sort of, I don't know, I wasn't happy with the simulation results, so I picked a voltage where I was happy. But let me go back and do, I don't know, 5.5, just to point out a few things for these first ones. Just the main thing I want to point out is that the current is in microamps, and I wanted it in milliamps. So I owe sort of 3 zeros in here. So the meter's reading 0.056 microamps, but I put it in over here 0.0000 to did the conversion, and the same thing over here for the 8. It was that I owed 3 decimal places to convert from micro to milli, so 0.008882. So I can carry on getting those statistics. I'm going to look at what is asked over here. Get the collector-emitter voltage divided by this current, sort of, I don't know, current, collector current, and that will be, I will be dividing volts by milliamps, so I'll be getting kilo-ohms. Okay, if I want to be fancy, I can insert the symbol and find my omega, Greek, omega, okay. And current over current here, there will be no units, it's just a ratio. So if I wanted to do this, VCE was the D, and I'm dividing it by this. And so this is sort of like a resistance. Well, it is a resistance. A voltage over current is a resistance. And it's like this sort of effective resistance of the transistor. And if I pull that down, we see that radically changing, that it was, this is kilo-ohms, it was like 5,000 kilo-ohms, and then drops down dramatically. And that is, the word transistor comes from transfer resistance. So that's what they do. They change their resistance, and it went from thousands of kilo-ohms down to, hundredths of kilo-ohms. And let me get this current ratio here. E divided by C in Excel. Copy that down. Okay. Then we want to look at the sort of some of the features of this. So if comparing VBE to the battery voltage, we see that for the first several rows, say up to a 0.05, they're almost the same to like the thousandth place. Or in this case, I guess that's the, that's the thousandth place. And then it begins to peel away. And then it kind of sticks at this 69.06.69. So we're getting sort of three regions, if you will. So if we were here, that this region I'll make blue, where these two are almost the same, and then this region over here where it sort of sticks at 6.9, and then sort of a middle range. So I would call this has the very high resistance. This is starting to change at 0.5, but it's still thousands. So we could have cut it off. Here, I'm not interested in like precise cutoffs, but just identifying roughly the three regions. So here's a region in where it was sort of sticking at 5,600. Here it's beginning to change, but it's in thousands. So you could decide this off region was 0.1 to 0.4 or 0.1 to 0.5. I don't think that matters too much. And then we have this region down here where we get that voltage sort of sticks at a 0.69. So we can think of this bottom of the transistor as a diode, and we need a bit of a voltage to get that diode flowing. But once it does, it sort of has a set voltage across it, and any other be here across this resistor. Okay, so we have sort of an off region, an intermediate transitional region, and an on region. I'm saying this is on because it's like flipping a switch. So we have a low resistance here, very easy to flow. We have a very high resistance here, difficult to flow. So I'm calling this the off, and this the on, and this the transition. We see here in this transitional region fairly consistent ratio of those two currents. So there is a way to use a transistor to amplify a circuit. So you can use it sort of if you sort of go from the on to the off, then you're using it sort of logically. But there is this, if you sort of stick to this transition region, you can exploit this ratio of currents being fairly consistent and use it to amplify a circuit. So there's a region of amplification, there's an off, there's a transition, there's an on. When you're working in the transition region, there is a sense where you can use it as an amplifier, whereas if you sort of stay out of that region and go from on to off, then you're using it more as a switch, more logically. So that's what I wanted to show you. Thanks for your attention.